Hey everyone, welcome to the lecture series of Elementary Classical Mechanics, where we will embark our journey from basic to advanced physics. Last lecture, we have learnt about derivatives and about the formulas. You can check it out since it's a prequel of this lecture. This lecture is about integration. I'm not sure I should call it as integration, rather, I should call it as integral calculus. Yes, I should, because the integration is the process of finding integral calculus. And in this lesson, I will explain the theory. So let's get started. What is integral calculus? It is a trend to say that integration is opposite of derivative, like antiderivative. I think the idea comes when we transfer the derivative from LHS to RHS, it transforms. But the concept of a derivative is quite simple, as we have seen in the previous lecture on theory of derivative. By considering the arbitrary point, drawing the tangent line from that point, it is basically a line drawn for finding its slope. But the motivation of the integral is that we can find the area under the curve of the function. Well, it is pretty complicated, but I'm going to use a conventional way to explain. It will be interesting. Before going further on understanding the area under the curve, first we must know how the integral calculus is represented. For the function to perform the integration on function f of x, it is by putting the long sloppy s kind like a symbol in front of the function fx, then multiplying by dx, and you know that when delta x tends to or approaches to 0, then we get dx. And you figured out that it is very small exchange, then added by the constant. Well, it is not an ordinary constant, I tell you that. This constant also has its name, constant of integration. Yeah, it is a funny name, and don't worry about the explanation about this. After how area is computed under the curve, I will right away explain the significance of this constant c. You know how I was talking about the opposite of derivatives in integration? Let us let us explore this statement. So first I take the function g of x, then find its derivative. So we write it as d of dx of g of x equals to the derivative of the function. Let's call it as a small f of x. Now let's take the dx to the right hand side. We get the form as d g of x equals to small f of x dx. Now just transfer the d from the left hand side to the right hand side. We get that slopey s sign and the constant. There are two types of integral, definite and indefinite. They are simple as they seem. For definite integration, the area under the curve can be found within the limits, and for indefinite, not so limit, to find the integration of the function f of x. Now, let us draw the function f of x equals to x on xy plane. Let us find the area under this curve, and it looks like a right triangle, which makes easier to find the area of the triangle cause we are already familiar with the formula. So for this triangle, the area is half into base into height. So here height and base both are 1, so the area will be 0.5. I have taken this simplest function cause it will be easier to prove, and calculating the area will be similarly valid for other function except some exceptions. A simple way of finding the area under the function will be placing the rectangular boxes under them. Then what we do is find the areas of all the boxes under the curve. So for that case, first phase of this experiment, we take 4 blocks of each width of 1 by 4 or 0.25. You can take any width, but taking smaller width will make more efficient with calculating area. For that case, we are taking 1/4 part of the whole length 1. Now moving forward, the height will be determined by the function f of x. So if x is at 5, then f of x is 5. In that case, f of x is height, so height is 5. If x equals to 1 by 4, then f of x is 1 by 4, and therefore the height is 1 by 4. Just keep in mind that f of x is the height at particular x value. Now we make the list for widths and heights. So for width, which is delta x, as we know, it is a change in x from final to initial position. So for first block, the delta x is 1 by 4, and height is at x equal to 1 by 4 is 1 by 4. So we get area as height into breadth as 1 by 4 multiplied by 1 by 4. For the second one, for the second block, the width will be same as 1 by 4 and height is 1 by 2. Since x is at 1 by 2, so height of the rectangle will be 1 by 2. Now the area of the rectangle will be 1 by 4 multiplied by 1 by 2, and we get 1 by 8. Similarly for the rest of the case. Now we got the individual blocks area. Now we just add them to get the area under the curve. Now what we do is find the area under the curve. We take all the areas of the blocks and add them, then we get the total area as 0.625. And area of the triangle is 0.5, and the value we got is not close. See, I blame the upper extra areas which were outside the curve. Don't you see? So I think I should reduce more width. So I will take less size of the width, less than 1 by 4. Now trying 1 by 4th block did not work so well. I will increase the stakes by adding 8 blocks for this length 1. This time each block is similar as before, but this time it will have the width 1/8. We now proceed by finding the areas of the rectangle. So we have 8 rectangles for varying height from 0 to 1. Similarly as before, the first rectangle of width is 1 by 8 multiplied by the height 1 by 8. Then again for second rectangle 1 by 8 of width multiplied by the height 2 by 8. Then third rectangle of width 1 by 8 multiplied by 3 of 8 height. So on for the rest of the rectangles, and we get 0.5625. See, I told you right that we are getting closer to the value 0.5. And you can see the extra triangles which we had trouble in 1/4 width. Now it's a little smaller this time. Now we got the area as 0.5626. See guys, I don't know about you, but I'm not satisfied with this area. So let's go further. Now we take 1 by 13th part of the length 1. Like we are making the blocks more smaller, in this case smaller to 1 by 13th parts. So when we write down all the areas of the rectangle and add them, we get 0.5383. Oh, now guys, we have extra 0.0383 extra area. They are reducing, right? You will hate it, but I have gone further to calculate for 40 blocks in between 0 and 1 length. Now x-axis, which makes it 1 by 40th the width of each rectangle. Wow. And when I calculate, we get 0.5125. 5125 guys, 0.0125 extra area to go. But if you have free time, you can go on calculating for smaller width. As we have calculated the area, we have seen that for the individual box area we have calculated by length into breadth, and then found out the sum of all the rectangles under the curve. So we get the generalized formula as summation of function f of x multiplied by the width dx. See, you know that from the last lecture on derivative, we have seen that delta x approaching towards 0 will be very small, and thus we just represent it by dx. Therefore we get the generalized formula as summation of sum of areas from I equals to 1 to n numbers for f of x multiplied by dx. This generalized form is called as Riemann integral. Now we know how we approached to this integral. Then this form we transform it into the integral form, such as summation of 0 to n as in sloppy s 0 to n for f of x multiplied by dx. This is form of definite integral, and this is indefinite integral, just the integral without limit. Significance of constant of integration. This may look trivial or non-important to you, but this constant is important, believe me. I have generated the graph for f of x equals to x squared plus c, and the value of c is changing from significant negative numbers to positive numbers. Guys, you may be thinking that this looks like not that much, but what you are watching is actually various families of curves. The curve is changing its position for different c value, and you will get different curves areas under it too. So the values of constant c will have a major effect on the function. And also, for the derivative there are infinite number of integral calculus, but for integral calculus you will have only one derivative. I upload video lectures within a week or two. Please remember to subscribe the channel. Your gracious subscribe will help me to create more quality lecture series. Phi Shastra will have the playlist of classical mechanics, and for continuing the lecture, please click on the floating card. Thanks and stay tuned.